In this example, I'm talking about find the state equation and output equation from the mathematical equation by using a controllable canonical form. So the mathematical equation is given. What is this mathematical equation representing? This represents a system. Okay, y is the output and u is the input. So u is the input, y is the output. This is the system. Okay, so if you remember, in S domain, y of s, h of s, u of s. So y over u, y of s over u of s equal to h of s. This h of s is nothing but the transfer function. Okay, it's nothing but a transfer function. What does it represent? It represents a system. So we derived this transfer function from a system. So when I write this equation in S domain, this is going to be s squared times y plus 3s plus 3s times y plus 2y equal to u. Okay, please do not confuse, my s looks like y here. So y over u equal to 1 over s squared plus 3s plus 2. That's the that is the transfer function. In time domain, if you want to write it down in time domain by using the inverse Laplace transformation, I can write this as 1 over s plus 2 and s plus 1. So it's going to be a over s plus 2 plus b over s plus 1. So by using partial fraction, you can find a value, a equal to, take the whole equation other than denominator of a, substitute s equal to minus 2 in that equation, you will end up with a equal to minus 1, and same thing, b equal to 1 over s plus 2, and substitute s equal to minus 1, b equal to basically 1. So basically y over u equal to 1, a is minus 1 over s plus 2 plus 1 over s plus 1. So when I transfer this into time domain, so this is going to be h of t equal to e to the power of minus 2t plus e to the power of minus t. Okay, so this is a transfer function representing, it could be a circuit, electrical circuit, or mechanical system, anything. Okay, now this is not, we are solving from there, we want to find the state equation, output equation, and he's saying that by using controllable canonical form. Okay, so what is the advantage of controllable canonical form? Whatever the state variables we're going to derive out of this, from the state equation, and we'll derive output from the output equation. But the main advantage of this controllable canonical form, whatever the model we're going to get out of this system, okay, is going to be controllable. That's the main advantage of doing controllable canonical form. Now, how do we do the controllable canonical form? So we'll take the mathematical equation. So let me write down the mathematical equation one more time here. This is the given mathematical equation, y double dot plus 3y dot plus 2y equal to u. Now what I'm going to do, I'm going to convert this y double dot equal to u minus 3y dot minus 2y. Okay, now I'm going to write down a simulation diagram. So since it's a second order system, you can see from the mathematical equation, basically we end up with a second order system, s square. The order of that system we can find out by using that mathematical equation. Okay, so it has two integrators. So two integrators, and here is my u and here is my y. If this is y, y is going to be here, this is going to be y dot is going to be here, y double dot. Okay, now to get y double dot, you have to have u, Okay, u is coming in minus 3y dot. So y dot is right here. Is that right? It's going to be minus 3y dot. So minus is there, that's 3y dot, and minus 2y, y is right there, so minus 2y. Okay, basically this is integrator, that's another integrator. This is the simulation diagram. So we know how to derive state equation, output equation from this simulation diagram. So if you look at the state, so two integrators, so I'm going to take x1 dot and x2 dot. So basically what we are doing here, we are converting a second order system into two individual first order systems, because it's easy to solve first order systems, even 10 first order system versus a 10 order system. It's easy to solve 10 first order system to find 10 variables. Okay, so that's the reason, that's what we are doing here. Okay, so now what is x1 dot from the simulation diagram? X1 dot is simply, can I say that is same as x2, and x2 dot is simply minus 3x2 minus 2x1 plus u. Okay, and y equal to x1, y equal to x1. So this is my output. Okay. These are my state equations and output equation, state and output equation. Okay, so from this I'm going to write it down in terms of matrix format or matrix format. So we know that x dot equal to ax plus bu and y equal to cx plus du. Okay, so I'm going to put a from this is, can I write x dot or x1 dot equal to 0x1 plus 1x2 plus 0u, and x2 dot equal to minus 2x1 minus 3x2 plus u. Okay, so same way y equal to 1x1 plus 0x2 plus 0u. So from this I can say a equal to 0 1 minus 2 minus 3, and b equal to 0 1, and c equal to 1 0, and d equal to 0. Though that's the state equation, output equation of that mathematical equation from a controllable canonical form. Okay, I'll stop this video here. I will solve more examples in the next video. Thank you.